Okay, we got any questions for today? This is a very, very light class. I definitely did not get that many emails saying people were going to the job fair, so. All right, so no questions before we get started, folks. If not, today is going to be on stability. We are switching topics here. All right, this is, I want to say it's chapter 6 in the textbook. But I kind of go off the beaten path a little bit for this one, at least for the first lecture here. All right, so the outline for what we're going to cover over the next, I want to say 4 lectures, maybe, including this one, is that we're going to cover definitions and criteria for stability, which I think is something a lot of you guys will be familiar with. And then from that point forward, we're kind of, for the most part, done with overlap with 3333. We're going to finally start getting into new topics like Routh-Hurwitz and the Routh-Hurwitz criterion. Maybe somebody taught that in 3333, but I don't typically. All right, then we're also going to go through the Routh-Hurwitz criterion. We'll have a few special cases for that. Then we're finally going to get into feedback control, which is like what this class is all about. And then we're going to see how Routh-Hurwitz, that criteria can be used for designing controllers, for controller design. All right, so today, maybe we can make this a shorter class. We'll see. Let's first by talking about our definitions and our criteria for stability. All right, so let's say we have a system y dot plus ay is equal to u. Let's say with u is equal to 0, and we have some initial condition for y. Let's say it's a positive number here. So we talked about this so many times. What is y going to look like as a function versus time? Give me some ideas here. Let's say our initial condition is, I don't know, it's like here, right? What is going to happen for y as a function of time for this case here? What do you guys think? And folks online, there are not a lot of people in class, so you guys are going to have to pick up the weight. Good chance to earn some participation in attendance credits today. So, anybody, what's our response going to look like for y as a function of time here? What do you think? You can go through and solve a little Laplace transform and all that sort of stuff, right? But at this point, we've kind of seen something like this enough times where you guys should know roughly what it's going to look like. What we got, folks? This is going to be a real rough class, guys, if this is going to be this way. I'm talking to folks.
A straight line?
Say again?
A straight line?
Straight line down, and then maybe it dies off. Good starting point. Not quite that way, but it may have, maybe not quite a straight line. Maybe it's going downwards. Exponential, that's the word I'm looking for, right? Thank you. So this is specifically an exponential if a is greater than 0, right? We can do this with our Laplace transform. We would find out our solution to y is y0 e to the at, right? And if a is less than 0, we're going to get an exponential decay, right? From whatever that y0 value is. Now, what happens if a is less than 0 here. And it should be actually, this is a negative AT here. What do you guys think happens in that case? There we go, right? We have a point here, and it's going to shoot off to positive or negative infinity and just go crazy, right? So if A was greater than 0, we head to an equilibrium, right? You guys remember that term, right? Which would be 0 in this case, right? And if A was less than 0, we head to plus or minus infinity, right? This is essentially a very basic way of describing stable versus unstable systems. This is specifically for a first order system, right? So let's talk about stability in the context of linear time invariant systems, right? Of any order, all right? So let's go through a few core definitions. All right, let's talk about stable. Right? So stable is the natural response of y approaches 0 as t approaches infinity, right? This again for LTI, linear time invariant systems, right? And it'll do this in an exponential fashion, right? It's all about the natural response, right? Not the forced response to our systems. This is what we do when we're talking about stability here. What about unstable then? Based off of that definition, what does unstable mean? Right? The natural response of y approaches plus or minus infinity as time approaches infinity. Right? Okay, one more definition. See if you guys still have this in your memory banks. What about marginally or neutrally stable? How many of you guys here or online, what have you guys heard the term more commonly? Marginally or neutrally? Neutrally? Okay. That's probably what that textbook covered. I'm going to use marginally. They mean the same thing here, though, right? Marginal and neutral stability mean the exact same thing. So what does neutral or marginal stability mean? What do you guys think? It oscillates, not necessarily. In a lot of cases it will, but that's not always 100% true, right? So let's go a little bit more general, but oscillation can be a part of it. It does not grow or decay, like on average, I guess we could say, but remains constant or oscillates around a value, right? So the natural response of y does not grow or decay. And I guess I should say on average, but remains constant or oscillates around a value forever, right? This is the border between stable and unstable, right? So let me see if I'm going to go through two different cases here. I don't think I will here. So let's cover two different options for marginal or neutral stability. One, as you guys have mentioned, right? An oscillation, something like this, right? That is one form of marginal stability, right? But another form of marginal stability could just be a constant, right? It's not shooting off to infinity. It's not going to its equilibrium or zero, right? It's just kind of staying there, right? A bucket that you fill with water, right? As long as it doesn't have any leaks and we don't talk about evaporation or anything like that, right? That dynamic would be marginally stable, right? The water doesn't slowly decay or grow in that bucket over time. All right. So how do we determine stability for a system? And let's talk about specifically in terms of our transfer functions, right? What do? How can we determine stability reliably, regardless if it's a first order system, second order system, 100th order system? Poles, keyword there, something about denominator I heard over there, roots, same thing as our poles, right? Denominator, root, right? The first thing you would do is get the characteristic equation, right? And for our transfer function, we've covered that before. It's when our denominator is equal to 0. When we have our transfer function in that proper polynomial over polynomial form, right? Right? It doesn't work if you have like a 1 over s down here, right? Setting that denominator equals 0 isn't necessarily going to give you what you want here. Right? So that's why I try and always enforce that polynomial form, or if you have your actual like roots set up directly there, right? Our characteristic equation determines stability, right? We use this to determine the poles, right? Like we have so far. And our poles tells us about stability. Right? Notice that we're always talking about our poles, right? Zeros, at least up until this point, for the systems that we've been looking at, zeros have nothing to do with our stability, right? The numerator of our transfer function does not determine whether we are stable or not, right? So what are the rules for our poles for stability? What are the rules for stability with relation to the poles? Right? Give me one rule. I'm looking for 3 rules total here. What was that? Complex roots are unstable? Not quite. We had an underdamped system, right, that we talked about before. That had complex roots, right? But that wasn't necessarily unstable, right? We did go down to 0, right? Thinking along the right lines, but not quite. The complex axis, can you like give it to me in terms of our poles here? Purely complex. Complex is, do you mean purely imaginary? Uh-huh. Okay, so what you just said, if all of our poles are on the imaginary axis, then we are neutrally stable. Not quite, but closer.
Negative green roots are stable.
There we go. So it's all about the real parts, with the exception of one specific thing here, right? Dominant root is positive. It is unstable. Yes, that's also pretty close here. Negative poles are stable. It's got to be, as somebody said up there already, I missed it, negative real parts, right? So if the real parts of all poles are less than 0, right, then the system is, for the context of this class, exponentially stable. Okay, that's our first rule. Now let's talk about that imaginary axis stuff here, right? Maybe that'll relate to our second rule here. So real parts, if they're all negative, then the system is exponentially stable. All right, so now maybe let's move towards neutral stability or marginal stability. Now, is it all of the real roots? Is it the most dominant? For my criteria, if any one pole has a real root that is 0, that is a neutrally or marginally stable system. All it takes is one, in my opinion. And generally that's how it's done anyway. If the real part of any pole, any one pole, is equal to 0, then the system is marginally stable, right? All it takes is for one to have a real part that's equal to 0, and then we're not going to go back to our equilibrium right off the bat. So even if we have 10 negative real poles, right, and then we have one that has its real part is equal to 0, that is a marginally stable system. Okay? All right, and then the last piece here. What would our last rule be? Maybe folks online, since you guys seem to be having a good grasp of this, right? We're probably looking for unstable, right? So we kind of have it there already. If the dominant root is positive, then it's unstable. If the real part is, well, not negative, then it's unstable. The real part is greater than 0, it is stable. The root is less than 0. We got to be careful here, right? If the real part of any one pole, of any pole, is greater than 0, or, and this is a special case, if there are any repeated imaginary poles, then the system is unstable, right? All it takes is one, because that one will become the dominant one, right? If everything else has a real negative part, they're going to 0, right? But we have one that's shooting off to infinity. We can't cancel that out, right? The dominant one is the one that's going to be positive, right? Regardless of how big or small that number is, right? Real positive part automatically makes it unstable, right? So it's like kind of like a ranking thing, and you could either start from the bottom or start from the top, right? If you want to start from the bottom, for example, you look at all your poles. If any one of them has a real positive part, it's an unstable system and you are done, right? You don't need to go further, right? Then you check if that's not the case. Maybe there's one that has a 0 for its real part. Okay, then it's marginally stable, right? And then you can check your final criteria. And if it's all the poles have real negative parts, then it is stable, right? So like this overpowers this, which overpowers this, right? For the second two criteria, all it takes is one single pole to meet one of those to ruin stability. Okay, question?
So, says repeated imaginary poles.
Yeah, so I'm about to draw that out here for a second, right? And if we have time, I'll talk about it a little bit more at the end of class, or I'll upload something here. It is a very special case. We may talk a little bit about it with Ralph Hurwitz. It's one I try not to focus a little bit too much on. But so, if we were to plot out real and imaginary here, for our first case, I'll just use black here, has nothing to do with complex. It's all about the real part. That's what determines stability. So if all the poles are over here, let's say something like this, this is for a stable system, right? That's system number one, we'll call it, right? But now, if I have a pole that's, let's say here, so different set of poles, hopefully you guys can see that purple, right? but then one here and one here, or one at the origin that is marginally stable, right? Because even though we have one with a negative real part, we have one with the real parts equal to 0, right? And that overpowers it. Then, if we have, let's say, one that's here and one that's here, this would be unstable, right? Even if this one over here was like over here or over here, doesn't matter. Either case, that is unstable, right? All it takes is just one pole to have a real positive part, and you have an unstable system. The extra case, let's see, use a different color here. I guess red will work. No, thinking of red. Good. All right, if we have a pole here and a pole here, right? And then we have another one right on top of it, right? So 2 at positive 2J and 2 at negative 2J, this will create another type of unstable system. Very special case here. And we'll, if we have time at the end, I'll go through at least part of the proof as why that happens. They are both on the imaginary axis. One is at positive 2 times I. A second one is at positive 2 times I. A third one is at negative 2 times I. A fourth one is at negative 2 times I, right? Because the imaginary ones always come in pairs unless they're at the origin. The origin is this part in the center here. Right. Any questions on that? Yeah. You guys speak louder. If it's at the origin, right, what's its real part? 0, so it is marginally stable. Right, we could do another case like that. Let's do cyan. We have one pole that's there and one pole that's out over here. This is marginally stable. Any other questions? Yeah.
You had a pole at -2, 3, 5.
Mm-hmm. -2, comma 3, so like here, and then -5, comma 3. You cannot have that because with the the imaginary part, they always need to mirror each other. So you would have to have one over here and one over here.
Yeah, that's what I'm saying. So like the imaginary part,
Well, they're the opposite, right? They have the opposite sides, right? This is 2i, right? Or what'd you say, 3i,
yeah,
right? It would have to have another one that has a -3i.
right. But those, so
But the real parts would be the same.
so the real parts are the same, but comparing 3 to 5, they have the same magnitude.
But the only way comparing 3 to 5, like if you're saying we have another set here, because they always have to come in pairs, right? You can't have one pole that's at -2, comma 3, and then -5, comma -5 or something like that. The real parts always need to be the same, and then the imaginary parts are the opposite of each other, right? It needs to be symmetric about the sigma axis. The top and the bottom need to be matching to each other.
There have to be 2 -3.
If you have a pole here, there is no way you're not going to have a pole down here.
Right. That's, but if you had another point above. But so is that system that we drew with those pole lines, is that stable?
This one? What are the real parts?
The real parts are -3 and -5. Imaginary parts.
All right, let me do another color here. Let's try lighter green. Okay.
There's the first one that
Okay, so just read them out to me.
-3, comma,
That,
5.
that. What do you guys think? Why stable? Right? It's all about the real parts here, right? These are not on the imaginary axis, so that is not the case of the repeated one. That is not the special unstable case, right? It's only on the imaginary axis when they're repeated that you get that unstable case, right? Otherwise, these bright green ones here, right? Real parts are all in the negative. Stable. That's it.
You had 2 repeating, it's at -3. Like,
Here,
yeah, like that.
but that's on the imaginary axis, right? It's specifically on the imaginary axis for that very special condition we may run into occasionally, but not very often. Okay. Is there a follow-up question there? No? All right. All right, so let's do some examples here. Let's just say we have a second order system. G of S is K over M squared, or whatever, the numerator isn't going to matter, right? MS squared plus CS plus K, right? What is our characteristic equation going to be? MS squared plus CS plus K is equal to 0. Typically in this type of problem here, if I ask for the characteristic equation, I wouldn't give you full credit if you just write denominator is equal to 0. If you have access to the full equation, write it out, right? And also the other part of it that some people tend to forget, characteristic equation, equate, you have to have an equal sign, equals to 0 somewhere in there. All right, what are our poles? What are our poles for this system going to be? All right, we've kind of done this one already. We're doing a second order system, but what we're doing here is going to apply regardless. What's our poles? P1 and P2. Right? I'm going to recommend you start sitting closer up to the front because you participate a lot and you got a lot of right answers, which that's not the important part, but you participate a lot and I never can hear you because you're always in the back. Yeah, but you could just sit there.
If we have to divide,
Do you need to in this case? I'm not looking for damping ratio, right? Or natural frequency. I'm just looking for poles. So no, you don't need to, right? You could if you want to, right? Maybe that's a lot easier for you guys to work with, but you don't necessarily need to, right? Quadratic formula, negative C plus or minus the square root of C squared minus 4MK all over 2M, right? If you wanted to divide by M first, you could have. If I was asking for a damping ratio or a natural frequency, definitely divide by M first. Okay, so example number 1 here. Let's say M is greater than 0, K is greater than 0, C is equal to 0. Let's say actually M is equal to 2, K is equal to 8 for our example. Tell me what we get for our poles. And tell me what type of stability we have for this system. Neutrally stable? Somebody said that. Who said it? Was you? So we got marginal stability as a guess. And why is that? Somebody got unstable? I guess I should write marginally stable. Negative 8J or 8I. Repeated imaginary poles. So I got plus or minus 2i or 2j here, right? C is 0, right? This comes from that 0. That's 0. Minus 4 times m is 2 times k is 8 over 2 times 2. Right? Forgot to divide by 2m. Yeah. Right. So we still have that plus minus there, right? What's the stuff in the square root? Was that 64? Negative 64, right? So this would be negative 64, which means we're going to have an imaginary part, right? If the square root has an imaginary part and our real part is 0, right? We're definitely going to end up with a marginally stable system, and we end up with plus or minus 2j here, right? And so if we were to see this system respond for a free response or an impulse response, in this case, we've talked about it, it would be oscillatory, right? Because we have those imaginary poles in our system. Okay. Any questions about that first one there? Right. For a second order system, what is this called? All right, we have different names for second order systems. Undamped, right? This would be an undamped system, right? The damping ratio or damping constant and the damping ratio is C is equal to 0, right? We can kind of see it there already. As long as it's not unstable, it's going to be an undamped system. This is marginally stable. Okay. Now let's try M is greater than 0, K is greater than 0, and C is greater than 0, but relatively small. All right, let's call M is equal to 2, K is equal to 10, and C is equal to 4. What do we end up with in this case? What are 2 poles? And what type of stability do we get here? Unstable? C is positive. Check your math on it. So C is positive, right? That doesn't mean that friction is adding energy to the system, right? We want C to be a positive number. If C is negative, that's when we get our problem, right? That's when we add force, even though we were originally trying to slow things down. Right. You're trying to do something in your head, which once we get through the next few lectures, I don't think we'll go through the proof for it, but what you're thinking about is something that for a second order system, we can determine stability just by looking at our coefficients. So you're a little bit ahead of the game here. So we have -4 plus or minus 2j, and somebody's saying that's stable, right? What do you guys get for your poles? -4 plus or minus 2j? Is that someone that's forgotten to divide by 2m again? Yeah? Same mistake? I think you forgot to divide by 2m, but otherwise it looks pretty close. So you forgot to divide by 2m for the first part. There we go. -1 plus or minus 2j. Or 2i. Right? If you guys were to guess what the response would look like for this system, what do you think? Right? What is that called for a second order system? What is this? Critically damped? Overdamped? How about somebody that hasn't participated yet? Which I think leaves these 3 and you, right? So we've guessed 2 of the 4 possibilities, right? Critically damped? Not quite. That's one of them. what are our options? Somebody underdamped, somebody online, I think they may have participated already, but I'm not certain enough to say that for certain, right? This is an underdamped system. It is also a stable system. Right? For second order, it's underdamped. All right. Let's try again. These three are all positive now, but C is going to be relatively large. So I'm going to say M is 2, K is 1, and C is 4. So C is relatively large compared to what those other two values of M and K are. What do we get for our poles in this case? Right, I'm doing this for a second order system for an example, right? But we could do this for third order systems, fifth order systems, 100th order systems. It doesn't matter. All this stuff applies for whatever order. Underdamped? So you would have to go back and look at your damping ratio, right? But you also, I think we went through last time, right? If we have complex poles for a second order system, right, and the real parts are negative, that is an underdamped system, right? We went through that, what, 2 lectures ago? Something like that, right? The best way would be to find the damping ratio. And if you went through and crunched out the damping ratio, in this case, you'd find it be under 1, but greater than 0. All right. If I'm asking for that, typically I'm looking for the damping ratio. But if you're familiar enough with the poles, right? Like I can just look at the poles for this system and say it's underdamped because I know they have to be complex numbers. So what do we get for our poles for this one here? Very good. Right? Is that J on it or no? No? Okay. Right? So what type of system is this? Or what's their stability, right? Square root of 2 over 2. Is that bigger or smaller than the magnitude of 1, right? That's the question here. Square root of 2 over 2. What do you think? Bigger or smaller? Smaller, right? Square root of 2 over 2, right? There's no way that number is going to be greater than 1, right? We have the square root of something under itself, right? So there's no way we're going to end up with a positive real part for one of our poles, right? They're both going to be negative. So what is this system? It is stable, right? If you were to guess, for a second order system in particular, what would this fit under? So we've already done undamped, right? And we just did underdamped. So we got 2 options left. This would be overdamped, right? Overdamped had 2 negative real poles, but they weren't the same value, right? That's what we went through last time. If you went and found the damping ratio, you would find it to be greater than 1 in this case. Right? So we would again have that 2 exponentials combined together. All right. Last one. M is greater than 0, K is greater than 0, and C is less than 0. So let's say M is 2, K is 10 this time, and C is -4. What are our poles? And what type of system do we have? What in terms of stability, I should say. So our poles are stability. And then also, what's that graph of y versus time going to look like? Just as a guess. That one's not as important. 1 plus or minus 2i. Do you get the same thing? Right? Why is it unstable? Positive real part. Exactly. Right? We have a positive real part. This is an unstable system. What do you guys think the response would look like for this? Just as a guess. This isn't as important. But how? Just like this? Or this? Right? So because, remember, oscillations are associated with imaginary parts, right? That's because exponential to an imaginary number, right? There's those, what is that, Euler formulas or something like that, right? Signs can be represented as exponentials with imaginary parts in it. So we would have an exponential growth to plus or minus infinity, but it's going to be oscillating the entire time, right? So this and this, right, our bounds would look exponential. I didn't draw very well. All right. Any questions on this stuff for our review of stability? Maybe in a different context than what you guys are used to. Okay. So, question for you guys, and then maybe I'll throw in one other thing at the end here, but major question, why is this useful? I'm going to ask that occasionally, every few classes from now on. What is the point of even bothering with stability? Any of you guys have any ideas for that? Or do you think it's just a wasteful topic that we just need to cover because I'm telling you to cover it in the class? Why is this valuable? What? Okay. So we got to vote for not useful. Right? So very good. Maybe you, I feel like you read the textbook or something already in this class, right? If we're going to design a controller, right, in the future, do you want, say, a temperature controller for your room? Do you want that to be stable or unstable, right? If I put in a set temperature of 75 degrees Celsius or 72 degrees Celsius, Jesus, Fahrenheit, right? Do I want my air conditioning to blast all the way down to like 32 degrees or something like that? No, right? That's an unstable controller. It's not doing its job, right? So when we're designing controllers or when we're just designing physical systems in general, right? You don't want to build an unstable system that's going to break and fall apart, right? Now, how could you determine whether that system's going to break and fall apart? Well, before you go through and build it, right, you may want to do some sort of numerical analysis, right? Like simulating the system. Before you even do that, just check your stability for the system, right? I didn't need to simulate this entire system to know that was going to blow up if I put an input into this, right? I just know, based off of my polls, that if I do anything with our system, it's going to blow up, right? Stability communicates a lot of information just by those basic numbers, right? It simplifies things a lot. That is at least one reason or a couple reasons why stability is going to be useful. And a majority of this class, I think in probably the class after or the Friday after the exam, we will design, I want to say then, our first stable controller for this class here. Okay, so stability, designing stable controllers is going to be a criteria from now to the rest of this class, pretty much. All right, 4, just because we have a couple minutes here, right? The special case I was talking about of repeated imaginary poles, right? If we had a transfer function, that's 1 over s plus j omega squared and s minus j omega squared, right? We'll say that u of s is equal to 1. It's an impulse. And let's say that parameter omega is equal to 1 here, right? Our poles, we have repeated values, on the imaginary axis here, right? I'm not going to go through the full derivation for it because somebody's done that years ago. But if we do an inverse Laplace transform of y of s in this case, which would be 1 over s plus j squared, s minus j squared, that input was 1 here, we would end up with a solution that is 1 over 2 times sine of t minus t times cosine of t. Okay? So what happens to this response over time? What occurs here in this very, very special, unique case? So we have a sine wave, right? That's never going to die out. Right? It's all going to be multiplied by 1/2. That doesn't matter too much, right? We have a sine wave that's never going to die out. That seems to indicate marginal stability here, right? So why is this unstable? Right? And what happens to t? Right? T is going to go to infinity, right? It's going to just keep increasing over time. We're not going to get exponential instability here, right? But this term will never die out. It's always going to be increasing, right? Cosine multiplied by t. And that means that this thing is going to grow forever. And that is our special case for an unstable system, right? Very specifically happens with repeated imaginary poles. Repeated, as in like there's two pairs, top and bottom at the same magnitudes, and imaginary. All right, that is it for today. Since we had a lot lower attendance here, I should say, but participation was good. As you guys head out, just put your name on the sheet. You'll get like a little bit of an extra bonus for participating. Same thing with the folks online. If you already put it in the chat, I mean, I have your names there. All right, so just make sure you guys put your names on here before you head out. That is it for today. Friday, we will continue with the Ralph Hurwitz criteria, I believe. So we don't have 10 more. All right. All right, I'm going to shut down the online thing here, folks.